We started last time, and I think we had an appropriately interesting and yet distracted conversation about entropy. But guys, today what we're going to do is we're really going to dig into the nuts and the bolts of this, and we're going to figure out how we need to understand disorder, entropy, moving into the tail end of this unit. Then guys, when I see you on Friday, we are actually going to wrap up the unit by bringing together enthalpy, which is what we talked about in chapter 5, and entropy, which is what we started talking about last time and we'll finish today. And guys, when you bundle enthalpy and entropy together, out comes Gibbs free energy. And guys, when we talk about Gibbs free energy, we are going to talk about it through the lens of the most important thing in this unit, which you all remember to be what? Spontaneity. So guys, on Friday, as we bring together enthalpy and entropy, we're then going to be able to have the definitive conversation about whether or not reactions are spontaneous, because the answer is actually Gibbs free energy. We'll talk. Then guys, when I see you on Tuesday, we will take our second unit test of the quarter. Then I will fast like a bunny, get those graded. I will get them back to you on Thursday. I will give you Thursday to rewrite your tests. And then if you do get done, also summarize chapter 6. This next unit is a 1-chapter unit, and it's really cool. It's all about electrons. Then guys, coming back, we will start the unit on Monday. And then guys, honestly, I don't know what we're going to do with Wednesday. It's a 45-minute class period. We may just get together and sing Kumbaya. I'm frankly not sure. We can't do content that day. The only thing that I could imagine is if we bleed over on Monday talking about electromagnetics, we may wrap that up on Wednesday, but we can't start talking about quantized energy and the stuff that we would do then. So I'll tell you more about Wednesday the 16th, depending on what Monday looks like. Go ahead, Alice. I missed the first part of what you said.
Like the 16th is not an A and a B day.
No. So that was the original thought, that it was going to be like that weird day we normally have before Christmas break where it's an A and a B mushed together. No, so, and I think did I mention this? So we just got this morning. It's 45-minute classes, school's out at 11, buses leave at 11:15. So, and it's just an A day. That's what we got. So guys, calendar thoughts or questions? Yeah.
So second term is just starting on a B day?
Yeah. And understand it's not a problem because we do semester classes. So we couldn't start third quarter on a B day because you have new classes, your half-year classes. But yeah, so second quarter begins on a B day. Yeah. And so guys, on the 16th, you all are done at 11. And then you also don't have school on Monday, so you have a 6.5 day fall break. That's not a bad deal. That feels pretty good. So, questions on the calendar? You guys good? Okay. So guys, let's do this. Grab your class notes. Yeah, we're not going to do that. Guys, grab your class notes. Let me grab this. And we are going to start. Got it. There we go. Sage, you with us? Here we go. So, guys, this is where we're going to start. I know that we talked about a lot of things last time. We got caught up in what's going on with the ice with the quick cold pack, which I still can't get to work. But guys, what I want to do is I want to bring us back to the things that we've got to agree on in order to move forward. So guys, let me take you through the things that we talked about last time. If you would like to add or amend or question any of this, please do. But guys, these are the things that we have to be able to mutually agree on in order to move forward. So guys, the first thing we agreed on is this. There are these things called spontaneous reactions. And what the thing that makes a reaction spontaneous is it happens without external intervention. And then guys, understand that we said that doesn't mean there can't be an initial input of energy, like burning Bunsen burner gas, you got to have a spark. But once we've added that initial amount of energy, that reaction happens on its own, and we call that spontaneous. Do we all agree on that? Is that okay? Okay. Then guys, we said something important. We said all spontaneous reactions. And guys, this is a hard all. All spontaneous reactions lose energy. Yes? We said that. And then guys, we had this conversation and, oh, sorry, I need my writing utensils. Guys, we had this conversation and we talked about examples of processes. Ooh, we're good there. Okay, so we talked about examples of processes that lose energy, and we talked about balls rolling downhill. And as that thing rolls downhill, it loses energy. And then we talked about hydrocarbons burning, and we said that as hydrocarbons burn, they lose energy. And then we talked about iron nails rusting, and we said that is also something that loses energy. Hard to perceive, but it also loses energy. And there's all these examples of things that lose energy and are therefore spontaneous. Y'all good on that? We agree there. Is that true? Okay. Then, guys, we had the quick cold pack crisis, because we understand that the very function of this thing is to not give away energy. That would make it a hot pack. But guys, this is a cold pack, which means by definition, it takes in energy. Endothermically, it takes in heat, it takes in energy, but it is also spontaneous, meaning that it takes in energy and we don't have to do anything to get it to take in energy. And if this thing didn't have a source of energy, it would still happen because this thing is endothermic. Are we all in agreement there? And then, guys, we had this crisis, and we said, oh no, how can that be? How can this be spontaneous? Because we've said that all spontaneous processes lose energy, and now we're saying that we've got a spontaneous process that gains energy, and how did we resolve that tension? Entropy. But if you remember the bridge to entropy, the bridge is this. Guys, this thing is losing energy. It's just not losing energy in the form of heat. It is losing energy in the form of disorder, which we call entropy. Go ahead.
So, is entropy its own separate thing, or is it like a form of heat or work?
That's a good question, and the answer is it is its own separate thing. They're all intimately tied together. Heat and work and disorder are all intimately tied together, but it's its own creature that is a part of that larger conversation. So all that we need to understand right now is that entropy is disorder. And guys, let me lay this at your feet for a second. Don't ever think of entropy in terms of order. It is not order, it is disorder. Why does it matter? It changes the sign. So you've got to, in order for your signs to line up, you've got to think of this as disorder. Go ahead, Addie.
So entropy is a way, is it a type of energy?
Yes.
So then why do the laws not apply to it?
They kind of, and the, yeah, so when we're going to talk. So is entropy like unto energy? And the answer is yes. We actually measure it in joules. You can measure the disorder of a system in energy units, which are joules. So why does the accounting not work the way that we've talked? And the answer is because there is not a law of conservation of entropy. There's not a fixed amount of disorder. There is a fixed amount of mass, there is a fixed amount of energy, but there is not a fixed amount of disorder in the universe. You're going to find find out that disorder is always going up. And we're going to talk more in a moment. Just a second. Caleb, go ahead. Are you okay? Go ahead.
Okay, so can entropy be transferred between things like heat and work can? Like, can it be used to change other things?
That's a good question. So how is disorder transferred? And I don't want to get into this too much because we haven't defined disorder yet. But what we can say is this. Disorder can actually be transferred through the avenue of heat. So for example, if you take hot water and cold water and you mix them together, it turns out that that hot water has higher kinetic energy, but also higher disorder because its molecules, microstates, its molecules are actually in more places at any given moment. So hot things have more disorder than cold things, and as they mix, they can transfer disorder. Okay, guys, are we settled? Are we feeling good? All right. So guys, what we need to do now then is we need to have a related conversation about all of this and this idea that relates back to the quick cold pack. So guys, why does this happen in the first place? Why does the quick cold pack work? I don't ask it rhetorically. Why does the quick cold pack work? Disorder's going up. If energy in the form of heat is going in, then guys, the only reason that this happens is disorder's going up. And so guys, we need to gather around that idea that some things happen simply because disorder is going up. So guys, let me show you an example of this. And I honestly just lifted it right out of the textbook, but let's talk. So guys, imagine this system. If you want to draw it in your notes, you can. That's up to you. Read the words in the... Can you read? Okay. So guys, what we have here is basically two gas cylinders. Think of them as balloons that don't change volume. They are rigid balloons. So guys, in this left-hand balloon, we have nothing. And in this right-hand balloon, we've got some amount of gas. We can measure the amount of gas in atmospheres. The pressure of that is 1 atmosphere. So guys, what are these gas molecules doing? Bouncing around like crazy, right? So guys, we've got a gas trapped on the right and we have no gas on the left. Now guys, here's the question. What happens if I remove the barrier separating one side from the other? What's going to happen? The gas will spread out. Now, here's the question. Do I have to heat this up to get the gas to spread out? No. Do I have to squeeze this to get the gas to spread out? No. So the gas will spread out. Spontaneous or non-spontaneous? We should call time out for a minute. Guys, one of the things that we didn't just review that we did talk about last time was spontaneous, reversible, and irreversible. I'm going to use those terms in just a minute to talk about this. If you need more clarification, we can do that. But I'm going to sprinkle this in as we go and use that as review. So, guys, the gas simply spreads out into both containers, right? And did we all just agree that that is spontaneous? Here's the question. Why? Why did the gas spread out? It's diffusion. It's spontaneous. Guys, why? Your silence is telling. Your silence is good because you are now being exposed to another driving force in the universe that you've got to wrap your arms around. Guys, why does the gas spread out? Did we do work on it? Did the surroundings add energy to it? Because guys, remember, there's only two ways for the surroundings to change the system. Those two ways are work and heat. Did we do work? Did we exchange heat? Does the gas still spread out? Why? It's more disordered. Guys, that is a valid answer to the question. It's the same reason the quick cold pack works. But guys, you've got to embrace this idea. The reason this happened is simply because it's more disordered. Now, I don't want to do this a lot, Daniel, but we're going to. Sorry, I keep pointing at you with this. Guys, it actually can be We're going to hear about microstates on the test. But guys, this is the idea. Imagine that we've got, I don't want to get too carried away with this. Guys, imagine that we've got, let's just do this with 2 and see if it's enough. Guys, if we've got 2 molecules of gas, we're going to call them molecule 1 and molecule 2. Understand that these molecules are moving, right? What are all the different ways? When we remove this barrier, what are all the different ways that these molecules can organize themselves? Given that they can freely travel, what could we end up with? Could 1 and 2 both be over here? In theory. What else could happen? Both could be over here. Or what are our other options? 1 could be here, 2 could be there. What are our, and then switch, 2 could be here and 1 could be there. Now guys, let's talk about what they look like. What would it look like if 1 and 2 were over here? It'd look like this. What would it look like if 1 and 2 are over there? It'd look flipped, right? The other side would have all the gas. But guys, what about these? What would they look like? The bottom thing. But how, of our 4 options, how many times out of those 4 options do we end up with something that looks like this? Half the time. Does that make sense? 25% of the time it looks like this, 25% of the time it looks like all the molecules are on the other side, and 50% of the time those molecules are evenly distributed between both. You get the idea? Now guys, let's do this again, only let's put 6.2 septillion molecules in the thing on the right, a mole, right? Because the idea is this. Every time you add another molecule to this demonstration, more and more of the time, like if we were to do this with 4 molecules, so 1 and 2 and 3 and 4, if we were to do this with 4 molecules, you would then find out with all the possible combinations, you would be more likely to have distribution that's equal and less likely to have lopsided distributions. And that only increases as the number of molecules goes up, till you finally get to the point where most of the time they're evenly distributed, and only a very small percentage of the time is the distribution in any way lopsided. Those are what are called microstates. And they explain the idea that when molecules are given the freedom to be wherever they want to be, they will generally pick states where they're more spread out. But guys, by definition, that condition where they're more spread out is higher disorder. If we've got 2 molecules in here, 1 and 2, that's relatively organized. But if we've got 1 over here and 1 over there, that is a higher degree of disorder, and therefore as it goes from this system to this set of conditions, disorder is going up, and all systems do that simply by a law of probability. What do you think? Yeah.
So is it a function of volume at all? Do you know what I mean? Like, you have the same amount of things that are slowly.
Like what if all of a sudden we made these half the size?
Yeah.
You'd end up with exactly the same results. They would spread out 50-50.
Okay.
Yeah, volume is not a function of this. The pressure would be higher, but you'd end up with the same results, yeah.
But is disorder affected by pressure, like it's affected by temperature?
Not much, not much, because remember, when we picture gases, gases are 99.9% empty space. So even as you start to compress these gases, disorder does go down a little because they're closer together. But the place where you really see a decrease in disorder is actually if you can compress it enough to get it to liquefy. So for example, you understand that canned air, this stuff, this is actually air in its liquid form. You compress it, can you catch? Yeah, you compress that hard enough, and that's actually air in its liquid form. It is much less disordered in the liquid form, go ahead and pull the trigger, than it is in its gaseous form. So liquids always have less disorder than gases. So there it's a function of pressure if you can get it to liquefy. Otherwise, it's really not. Is that okay? Get the idea? Okay. So guys, are you beginning to get comfortable with this idea that things can happen simply because disorder goes up? Okay. So guys, if you're comfortable with that, ready for this one? Ready? Life-changing stuff coming at you. Ready? Salt. Oops, wait. Oh, this is the wrong screen. This one. Guys, salt dissolves in water. No, it's true. Salt dissolves in water. But guys, here's the thing that's interesting. When we say salt, we're talking table salt. And guys, you've probably never done this, but you're going to in lab next week. Guys, when you dissolve salt in water, does it get hot or cold? It actually gets cold. Yeah. It turns out that when table salt dissolves in water, there are other salts that get warm. But when table salt dissolves in water, it actually gets cold. But we know that table salt dissolves in water. Is dissolving table salt in water spontaneous? It is. But it's also endothermic. So why does it happen? There's an increase in disorder. Guys, what I'd like to do is I'd like to play for you the video of salt dissolving in water. And guys, when you watch this video, I'd like you to watch it with new eyes. Look for changes in disorder, up or down. There's a lot. Guys, look for changes in disorder.
When an ionic substance, such as sodium chloride, is placed in water, water molecules interact with the ions on the surface. If the salt is soluble, the attractive interactions with water molecules overcome the ionic attractions within the lattice. The solvated ions move off the surface and become separated in solution. Notice that water molecules cluster about the anions with the hydrogens directed toward the negatively charged ion. On the other hand, water molecules interact with the positively charged cations through the lone pairs of electrons on the oxygens.
Got it? Let's do it again. So guys, when we start the video, we start with a salt crystal, a lattice. Guys, talk with me about entropy. Talk with me about disorder for a salt crystal. Highly disordered, low disorder. Yeah, guys, crystalline solids, by definition, have very, very low entropies. I mean, I can show you the model. Guys, these dudes are super organized. That's what makes them crystalline. So this has a relatively low entropy, and you can see that. Because guys, just as we understand generically disorder, this is not very disordered. You sold on that? Okay. Now guys, let's continue the video.
Ionic substance, such as sodium.
Kill the audio. So guys, now we're putting this in water, liquid water. Liquid water looks something like this, but we realize they're moving. But guys, what about the disorder of liquid water? Relatively high, right? Could it be higher? Yeah, if we turn it into steam. But guys, liquids are relatively high disorder systems. The entropy is higher. But now guys, as we continue to play this little animation, now the question that we can ask is, what is happening to disorder? What is happening to entropy? So guys, what's happening to entropy as this goes? Is it going up or down? What is happening to entropy as this goes? Is it going up or down? Both. Yeah. So yeah, and that's the thing that we forget to take into consideration. Guys, all of you said up, but what were you looking at? The salt. And guys, as the water rips the salt apart, the entropy of the salt is going up significantly. Again, this idea that now these molecules, these ions are in so many different places and the entropy is going up. But I said both. So what's going down? The entropy of the water. And guys, actually, they do a really nice job of showing this in just a second. Because all of a sudden, we can see that these water molecules are organized. And as those water molecules get organized, and guys, this is about to flow into a really big idea. As these water molecules get organized, what is happening to their entropy? It's going down. So here's the question. Which is greater, the increase in entropy for the salt or the decrease in entropy for the water?
Well, if it costs to be, then it has to be the salt.
Hold on, think about it for a second. Which one is greater? The increase in entropy for the salt or the decrease in entropy for the water? And ponder it for a moment. Talmud, you're saying salt. Why salt? And that's all of the, actually not quite all the answer you need. But guys, that's where the conversation starts. Think through this logic. We know that salt dissolving in water is spontaneous, right? If it's spontaneous, we know that it's giving off energy. But does it give off that energy in the form of heat? No. How do you know? Because I told you it's endothermic. So guys, if it is not giving off that energy in the form of heat, it is giving off that energy in the form of disorder. Disorder is going up. And what in this process is the going up entropy process? The salt breaking apart. So guys, what we know is this. You ready for a big idea? The amount of energy being released as the salt becomes unorganized is greater than the sum of the heat absorbed by the process and the organization that's taking place as the water gets organized in clusters around the ions. Crazy, right? So guys, how do we bring all that together? How do we bring together that math of entropy up and heat in? And the answer is Gibbs free energy. We're going to quantify that on Friday, but for now we're just going to say this. The amount of energy that is released as the salt gets mucked up is greater than the energy taken in because this is endothermic and the energy that's going in as the water gets organized. It's greater, and we know that because the reaction happens. Guys, understand it's not exactly this simple because there's also a temperature term in here that we need to talk about. We'll do that on Friday, but that's the logic behind it. Are you settled on the ideas? Okay, so guys, what we need to do then, and I'm going to, if you'll forgive me for a second, I'm going to hop out of my notes because this actually ended up in the wrong place. And now we can do this. Okay, so guys, let's now finally wrap our arms around what we're saying about this idea of disorder. And guys, you want to get this in your notes. So guys, when we talk about disorder, we are talking about entropy. And guys, please, 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 it's never about order. It is always about disorder. Now guys, entropy, sadly, is abbreviated S. I know. You're okay. And guys, it's important then to understand this, that the more disordered or random Now guys, what we're about to talk about actually is going to sound kind of stupid, but it is important that we talk about it. So guys, the thing that we need to wrap our arms around then is this, and it really gets to Addie's question that she asked a couple minutes ago. Why haven't we been taught, and I'm in a horrible paraphrase, Addie, forgive me, but how do we deal with this idea of entropy lost and gained? And guys, what we're saying is we don't think of it as entropy lost, entropy gained in the same way that we think of energy lost being the same as energy gained. Guys, it turns out there is not a law of conservation of entropy. Instead, when we talk about entropy changes, we're where did this come from? Oh, when we talk about entropy changes, we've got to look at the entire thing. So when we talk about this idea of looking at the entire thing and it comes together in the thing we just talked about, guys, when we talk about salt dissolving in water, it's important that we look at all the entropy changes that are going on. So guys, the idea is that as the salt dissolves in water, and if you already understand this, don't write it down. It's a reflection on what we just saw. As this happens, we know this is endothermic. Therefore, it shouldn't be spontaneous, but we know that it is. So guys, the thought then becomes that disorder is not conserved. The amount of disorder that the salt increased is not the same as the amount of disorder the water decreased. And guys, it turns out that as this took place, the disorder of everything actually went up. So guys, the idea then becomes this, and you may want to write this down. When we talk about disorder, and this is different, we need to consider all of the organizational changes. We've got to talk about all the parts of the system. And when we do that, many times we're going to have ordering and disordering processes. In this case, the disordering process was dominant. But guys, when we look at disorder, entropy, we need to wrap our arms around not just the system and not just the surroundings. Because as we know, things can become disorganized without external intervention. Disorder can go up without it coming from anywhere. It just happens. And it's a driving force. So guys, there's actually one more thing that we need to talk about as we wrap this up. We're going to be done in like 10 minutes and you're going to get your homework done today. That was purposeful. I was actually thinking about crushing through this and doing Gibbs free energy and us doing the test on Friday, but I really want to give you time in class to get this homework done, so that's what we're going to do. So guys, this then is how we're going to wrap up the day, and then we'll get our arms around Gibbs free energy next time. So guys, this is what is called the second law of thermodynamics. Again, promise me you won't look it up. By the way, we could review really quickly. Guys, what is the first law of thermo? Energy conservation, energy lost, energy gained. Guys, I bring that up because the second law of thermo is not entropy conservation. There's no such thing. So, guys, this then is the conversation. When we talk about entropy, unlike enthalpy, when we talk about entropy, we've got to think about the system and the surroundings. You ready? Yeah.
So when we're talking about the system and surroundings, we're looking at it in the chemist's point of view, like that we're in the system.
At this point, it doesn't matter, because we're now broadening our position, and so what we're talking about is the universe. So system plus surroundings is the universe, and when we talk about entropy changes, our location becomes less important. You're right that when we talk about entropy up or entropy down, we will be in the system, but it's important when we think about entropy changes in general that we see the whole thing. So probably, Tucker, you're fine. Keep yourself in the system, but don't ignore the surroundings. And you'll see in just a second. So guys, when we think about entropy changes, we actually need to broaden our horizons, and we need to talk about the entropy change of the entire universe. And when we do, this takes into consideration the entropy change of the system and the entropy changes of the surroundings. And if it's more comfortable this way, instead of writing down this sentence, you could probably just write down this oversimplified equation, that the change in entropy of the universe is equal to the change in entropy of the system plus the change in entropy of the surroundings. Now guys, this seems kind of silly until we relate it back to some interesting and familiar ideas. And this is how we're going to wrap up today. You guys all caught up? You okay? You're good? Okay. So guys, first of all, let's consider a reversible process. I would strongly encourage you to write this down. And maybe now would be a better time to remember what reversible means. Would it be worth going back to that slide and remembering? Yeah? May I? Because I really think for 2 minutes, it may be worth doing this. I'll come back to this in a moment. So guys, when we talked about reversible and irreversible, here's what we said. So we can describe processes as being reversible or irreversible. Now guys, without reading my slides back to you, let's talk. So guys, when we talk about reversible processes, is anything taking place? Well, yeah. What is actually going on is the forward process and the reverse process are happening reversibly at the same time. And we have a name for that, right? We call it equilibrium. So guys, when a system is at equilibrium, both the forward and reverse processes are happening at the same time. We call that a reversible process. Now guys, from a spectator standpoint, if you look at something that's reversible, can you tell that anything's changing? No. The net effect is no change because the forward and reverse processes are undoing each other. So if you look at a reversible process, it really looks like nothing's happening because what is actually happening is the forward and reverse they're undoing each other and it looks like nothing's happening. Those are not spontaneous. So guys, and that's where people get stuck. Because they're like, wait, something's happening on its own. Isn't that spontaneous? And guys, the answer is no. And the reason that reversible processes are not spontaneous is because they're not going anywhere. They're going in circles and they're not spontaneously creating an overall change, so they are not spontaneous. You can kind of think of them as being simultaneously spontaneous in both directions, but by our definition, they are not spontaneous. So then, guys, we've got irreversible reactions. These are reactions that go in one direction, but they don't go in the other direction, like balls rolling downhill and nails rusting and all these other things. Guys, these are irreversible processes. They go one direction and they never go the other direction on their own. Now guys, does that mean they can't be made to go the other direction? Sure they can, but what do you have to do? Work. And guys, that's the point, that irreversible reactions have a direction they always go and a direction they never go on their own. They can go that other direction. That's what it mentions here. They can go backwards, but they go backwards through a different pathway. Those are what are called irreversible processes. Do you see the difference? Okay, now guys, the thought then is this. Spontaneous reactions are the irreversible one. And we talk about those as having a spontaneous direction. So irreversible reactions have a direction they always go. We call it the spontaneous direction. And then they have a direction they never go. And that's what makes them irreversible. Is that okay? All that said, okay? Okay. So guys, with all of that said then, let's come back to this and tie this all together. So guys, if you've got a process that is reversible, at equilibrium, is anything happening? You can't tell, but what is happening? This, right? So guys, if this is happening, maybe now would be a good time to remember if this is helpful. Do you remember the example we used for equilibrium reversible? Ice water, right? And guys, we talked about this previously in terms of heat. And we said water molecules with more kinetic energy crash into here, they freeze, they lose the energy to the ice, and one leaves, one in, one out, equilibrium, right? At 0 degrees Celsius. But guys, what do you suppose is true of entropy? with water sitting there at 0 degrees Celsius, which has lower entropy, the ice or the water? The ice has lower entropy. So guys, if the ice has lower entropy, but for every water molecule that freezes, one melts, what would be the overall change in entropy as this goes on? 0. And guys, that's the point. If you've got a process that's at equilibrium, the change in entropy of the universe is 0. The gains and losses cancel each other out. Doesn't that kind of make logical sense? Heaven forbid logic would ever drive anything we do in here. But in this case, it works. So now, guys, let's do this to wrap this up, and then you're going to have like 30 minutes to work on your homework. So order is conserved. So what about irreversible and therefore spontaneous processes? What do we think is going to be true of the entropy change? And guys, it's greater than 0. In any process that happens spontaneously, the entropy change of the universe is going up. So guys, order is not conserved. If we've got spontaneous processes, order is not conserved, and the disorder of the universe is going up. So guys, at this point, we're going to have sort of a weird conversation, and then we're going to call it a day. You okay? Are you all caught up? Okay. So, guys, the conversation goes like this. You understand the difference between reversible and irreversible reactions, right? If you see a reversible reaction, what are you actually seeing? No change, right? To our eye, nothing is changing. If we see an irreversible reaction, and we're actually not going to call them irreversible reactions, guys, if we see an irreversible reaction, that's spontaneous. And those are the things that we see. So guys, here's a weird thought. Everything that we see around us is really just a chemical reaction. Whether it's light energy coming out of light bulbs in the form of light, whether it's me moving around, burning through calories and turning that into motion. Guys, whatever it might be, your car running down the road, burning gas. Guys, think about this. The only things that we ever see happen are spontaneous reactions. Think about that. The only things that we ever see happen are spontaneous reactions. Do we ever see equilibrium reactions? Sure, but we can't tell that anything's happening. Do we ever see reactions that go in the non-spontaneous direction? Not spontaneously, unless we drive them. And so, guys, the idea here is that the things that we experience that make up our reality are reactions that are happening spontaneously. Now, here's the thing that's interesting. Guys, what about reactions that create order? What about reactions that create order? Like, for example, trees growing. Guys, how does a tree grow? What are trees made of? Carbon and oxygen, right? And it takes the carbon dioxide out of the air, it takes the water, puts those things together, makes molecules that then make trees, right? Guys, life is actually an organizing process. We take atoms out of our universe and we organize them into things that make up us. And guys, this happens all the time. So we've got these organizing processes that take place all the time around us, but we've also got this rule that says the disorder of the universe is always going up. Anytime something happens, guys, even if it's an organizing process, if it happens, there has to be an offsetting increase in disorder somewhere else. So where is that somewhere else here on Earth? You ready for the deep thought? It's the sun. Guys, we think of the sun as a source of energy, right? because the sun is also a source of disorder. As the sun gives off energy that we experience as heat, the disorder of the sun is actually going up. And the increase in disorder in the sun is always enough to offset any organizational processes that are happening here on Earth. And consequently, even life doesn't violate the law that disorder is always going up, because there's always some disorder being created in the universe anytime a process takes place. Now, guys, I know that's kind of weird, but we got to think about that coming back to this idea of the second law of thermo. We haven't stated it, and we're not going to in writing, but here's the deal. The second law of thermodynamics simply says this: the disorder of the universe is always going up for any process that takes place. And if we can't immediately see where that disorder is going up, we can always track it back to the sun, because that's where we get the energy for the processes that take place on Earth, and there's always an increase in disorder there. So I know that seems sort of distant and weird and almost metaphysical, but guys, understand it explains the second law of thermo, because the second law of thermo says disorder is always going up. Is that okay? Kind of weird, right? But that's the underlying idea. So, guys, with that said, we're going to tackle these in homework, and you have the time today to do this. You've got 30 minutes. And guys, I'm not going to let you stray. No phones, no headphones, none of that stuff. Guys, we're going to focus and we're going to get this work done. We will grade this on Friday. We will quantify entropy. We will quantify entropy on Friday. We will talk about Gibbs free energy on Friday. And then so let me put this away. Josh, I'm going to, just one second. So save that, quit this.